Problem 3.51. In this problem, there is air that is drawn into the wind tunnel used for testing a car as shown in the figure below. We need to determine the manometer reading h when the velocity in the test section is equal to 60 miles per hour. Note that there is a 1-inch column of oil in top of the water in the manometer. We also need to determine the difference between the stagnation pressure in front of the car and the pressure in the test section. Okay, to start this analysis, we are going to choose the test points we're going to use. So we're going to use far away before it enters to be 1, the test section right in top of the manometer is 0.2, and the top of car of the section to be 0.3. Okay. We are going to assume that this is going to be a steady state case. We're going to treat the fluid to be incompressible and inviscid. And the 3 points are along the same streamline so that we could apply Bernoulli's equation. Okay, so we're going to enter the information that we have for the 3 points. In terms of pressure, velocity, and elevation. So the pressure at point 1, we take it that is far away, so it's going to be atmospheric pressure. The velocity that we are going to have at the pressure at point 2 is one of the things that we need to find out. Same thing as point 3. The velocity at point 1, we assume it to be 0. It's not moving. It's only until it's being absorbed by the testing facility. So at this moment, it's also going to be 0. Over here, it's going to be 60 miles per hour. And over here is in stagnation velocity or stagnation point, so the velocity is 0. And the only thing that we know about the elevations, we consider them to be the same. Okay, so we are going to start with our Bernoulli equation between points 1 and point 2. Okay, that allows us to relate those 2 points in terms of pressure, velocity, and elevation. So we do P1 plus gamma Z1 plus 1/2 rho V1 squared is equal to P2 plus 1 plus gamma Z2 plus 1/2 rho V2 squared. From here, we're able to cancel the pressure, point 1, the velocity at point 1, and we also are able to cancel the 2 elevations since they are the same. And we solve for the value of the pressure. Pressure at point 2 is going to be negative 1/2 rho V2 squared. And notice that it's going to be negative, and the reason is because this is being taken from the fan. It's basically being absorbed, being sucked in. It is a vacuum pressure. So we solve for the value of the pressure. P2 is equal to negative 1/2. The density of air at standard conditions is equal to 0.00238 slug per feet cubed. And the value of 60 miles per hour, it is transferred into feet per second and becomes 88 feet per second. And we square it per the equation. And that gives us a value of the pressure to be 1.22 pounds per feet square. Now that we have the value of the pressure at point 2, we're going to use the manometer to get the value of the reading H. So I'm going to try to redraw this manometer. And then we have 2 different fluids. This is going to be water. And it goes all the way to here. Okay. And then we have oil here. This elevation is 1 inch. We're going to call it simply H1. And the elevation that we have over here, which is what we're looking for from here to here, is going to be H. And this is oil. Right? So we know that the value of the pressure that we have at the testing over here is P2, the value that we calculated, because the fluid that we have from the testing to the manometer is going to be air, we assume that the pressure from here to here is about the same, because there is going to be a very small pressure variation inside of air due to its low value of density. So then when we have this, we are going to be able to find the value of the elevation. So now let's evaluate P2 from the point over here. So this is point 0. We're going to take it to P0, and that we know that is an atmospheric value. Then we write the pressure goes, elevation goes down, so it's positive gamma of the oil times H1, and then from here it goes up minus gamma of water H. We said that P0 is equal to 0, so we cancel it out. We know P2 is equal to gamma of oil, and the gamma of oil, the specific gravity is given, so a specific gravity times gamma of water times H1 minus gamma of water H. And so we're going to solve this for H. So P2 minus Sg gamma of water times H1 is equal to negative gamma of water times H. So this becomes simply getting rid of the negative. We have Sg gamma of water H1 minus P2 is equal to H all divided by gamma of water. Okay, so now let's substitute the values that we have. The value of the specific gravity is 0.9, 62.4 pounds per feet cubed. The elevation H1 is 1 inch. We transform to feet by divided by 12 inches, gives us 1 foot, minus the value of the pressure that we obtained in the previous value, negative. So notice that it's negative 9.22 pound per feet cubed, 5 feet squared, sorry. And we all divide this by 62.4 pounds per feet cubed. And that tells us that the elevation that we get in this particular case is going to give us 0.223 feet. So that's the elevation of this column that we have in this part over here. So once again, the value of that is 0.223. The second part of the problem is ask us to evaluate the pressure difference between 0.2 and 0.3. And we do the same process. We're going to do Bernoulli's between those 2 points. So we do P2 plus gamma Z2 plus 1/2 rho V2 squared is equal to P3 plus gamma Z3 plus 1/2 rho V3 squared. We know that this is an stagnation point, so the velocity is going to be 0. The positions are going to be the same. And therefore, we find the pressure difference between P2 minus P3 equal to, so let's actually do P3 minus P2 so that we have a positive value. To be equal to 1/2 rho V2 squared. And we already have that value. We calculated it previously over here. Notice that we have, it's only that is positive, but the delta of this pressure is the same, 9.22 pounds per feet square.